Oh, black holes. All right, here we go. Let's talk about black holes. First of all, in a sun, there are two main processes. One is gravitation. And gravitation is trying to pull everything into the middle. Meanwhile, inside the sun is something called thermonuclear fusion. A little warm. But it is an outward force. And in a normal sun, these two forces balance. And therefore you get a sun that has a pretty solid, normal size. You know, it stays the same. I don't mean that, particular size. I mean that it doesn't change sizes. So our sun right now is totally balanced between gravitation and thermonuclear fusion. And so the size of our sun does not vary. It stays the same. Okay? So there's this tug of war between those two. And as long as those two are the same, then the sun doesn't collapse or the sun doesn't explode. Neither one of those are a good process. Okay? But what happens if the fusion rate increases? Well, then the sun's going to get hotter. And if it gets hotter, thermonuclear fusion will cause it to expand. It's going to get bigger. If the fusion rate decreases, the sun's going to get cooler and it's going to get smaller. So eventually, our sun, or any sun, will run out of fuel. And when it does, gravitation wins. Because gravitation doesn't require fuel to keep it going. Gravitation is just a property of all matter. And so once that gravitation starts winning, once our sun runs out of fuel, the sun will start to collapse. Okay? And then what happens is our sun will start to burn helium and fuse that into carbon. Now that process will cause our sun to become a red giant. So it'll expand. In fact, it'll be so big, we would actually be part of the sun. It'll expand and consume the earth itself. Eventually that helium is going to run out, and then our poor sun is going to collapse. And then, it's used up all of its fuel. It now becomes what we call a black dwarf. Now, this is not a black hole. This will simply be basically a sun that's burnt out. So just a big rock in space is what it's going to be called, or what it's going to be. That's what that is. It's just going to be a big, huge rock, probably made up primarily of carbon and other heavier elements. But it will no longer be able to continue to give off light, continue to have that thermonuclear fusion take place, and so it'll just be there. Okay? Now, if the star is bigger than that, if it's about 2 to 3 times bigger than our sun, then gravity is a lot stronger and it can actually continue to pull those in. So instead of becoming a black dwarf, it will actually have so much gravity that the atoms will be pulled in on themselves. They will collapse. You know how we talked about how here's my nucleus, and, here's my electrons way outside here, and that's not even big enough really. Well, what's going to happen in a black hole is these are going to be pulled in, so everything's just going to be in the nucleus, basically. There's no going to be electrons running around outside, and it'll become very, very dense, infinitely dense, and we call those black holes. Okay? So they're so dense that not even light does not have enough velocity to escape it. And so that's why it's known as a black hole. But the thing about a black hole that people always say, oh, everything's going to get sucked into the black hole. No, you know what? Not any more than we're being sucked into our sun right now. If you're in orbit around a sun and that sun gets changed into a black hole, the gravitational field is exactly the same as what it was before. You could still orbit that black hole. It's no different. There's no more mass. Therefore, there's no more gravity. All it is the mass is all in one small area so that anything near that can't get away. So here's our, a star. Hey, we're orbiting around here. No big deal. Even if it's a black hole, we're still going to orbit around there. The only thing is we're not going to see any light from that black hole, so it'll be pretty dark, but it's not going to change the amount of force that thing has. You see a lot of these pictures that kind of indicate the black hole, but really, things aren't going to be sucked in any different than they are in real life or right now around the sun or anything like that. So if you could take your spaceship and fly around the sun and get away, you can get to that area like that. You can still do that with a black hole. It's not any different. However, if you got too close, then you would disappear from us and we would never be able to find you again. While we can't see black holes, we can find or see effects of them because a lot of places are binary systems. In other words, there are a lot of stars that are two-star systems. And what we find is that these things tend to rotate around each other. And so you've got this, you can actually measure the wobble that these things move. For us, being so far away, you can't really tell that they're really rotating around things, but we can kind of measure a little bit of wobble seen by that as they go around. So we can kind of see that those things are accelerating or going around there. Now, if one of those is simply a black hole, we can still measure that. And actually what happens is as this light and energy is given off and sucked into the black hole, X-rays are given off that are detectable, and you can actually kind of measure that. So they can kind of detect energy that's being sucked into the black hole. Inside the center of most galaxies are these immensely massive black holes. If their calculations are right, they could be maybe more massive than millions of suns. So in the center of our galaxy, we've got our galaxy. What do we got here? We got somewhere in the middle here is a giant black hole. Millions of suns big, or small. All right. So the Earth is round because of gravity. Because everything attracts everything else. So the Earth was kind of, pulled together. The sun, the moon, the Earth, all are spherical. That's why planets, that's why stars, that's why things are spherical, because of gravity. It tends to pull things into the smallest location, tries to get everything to the middle. And we talked about this if you're in physics literacy, as things start to spin, they're being pulled in. Or the other day we talked about angular momentum. If you're spinning, you have angular momentum. And as these things are being pulled in, if all the matter is inside smaller, this thing has to spin even faster as it's doing that. So it tends to then become a spinning disk. And that's why we have galaxies that look like that. That's why solar systems tend to be flat, in a sense. They tend to all be in pretty much the similar planes if you look at different solar systems. So that's kind of why, because you have this angular momentum as things start to spin, and that's how these lumps kind of become either stars or planets or whatever. Okay. All right, so let's talk about big word here, perturbations in the solar system. Okay, so if everything pulls on everything else, then the planets must pull on each other. So the net force that controls Jupiter is not just the sun, but it's also us, it's Mars, Neptune. All these planets have a little bit of an effect. It's small compared to the sun, but it's still there. And those deviations are known as perturbation. Okay. So until the middle of the last century, astronomers were really puzzled by the perturbations of the planet Uranus. So now I dare you to go home and tell your parents that you were studying about Uranus's perturbation and see what they say. Anyway, back in 1845 and 1846, a couple of guys, John Adams, Urbain Leverrier, whatever, were studying this, and what they decided was, there's got to be something out there causing these fluctuations in the planet Uranus. Well, eventually, that was how they discovered Neptune. So yeah, there's something out there. Okay. Shapes of distant galaxies provide further evidence that the law of gravity applies to larger distances. We've talked about this. This is more stuff we're going to talk about in briefer history of time. But, Big Bang Theory, the whole idea, that there's this big explosion 13.7 billion years ago, kind of everything's accelerating outward. What's interesting is they talk about this idea of dark energy because we have a problem, The universe is continually expanding, not slowing down. Well, we know gravity should be pulling everything back in. If it started here and everything's exploded out and everything has gravity and gravity's going to pull it all back to the middle, but it's not happening like that. So they think that there's this stuff called dark energy that they say makes up about 73% of the universe. And there's other stuff called dark matter, which makes up about 23% of the universe. And how they know this, I have no idea. But they believe that the universe couldn't be, or our galaxies couldn't continue to be expanding without some of these things around. So that's kind of some interesting things that are happening out there in cosmology, I guess, right now, today. All right, so getting back to universal gravitation, Newton, there's very few theories that have had as big an impact on science as gravity. This obviously has been a big one, for us. All right.